Welcome back my dear friends, a very good morning, good afternoon, good evening to all of you wherever you are in this part of the globe. And as you know, this is the DADM 3 as you can see in the slide, which is data analysis and decision making 3 course under NPTEL MOOC series. And this course total contact hours is 30 hours spread over 12 weeks, and if you convert into the number of lectures, considering each lecture is for half an hour, this is total 60 number of lectures. And as you can see from the slide, this is 25th lecture, which is the end of the 5th week. And each week you, after 5 lectures, you take an assignment. So, you have already taken 4 assignment, with the end of this you will take the 5th assignment, and after the end of this course for 12 weeks you will take the final examination. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, if you remember in the 24th lecture, at the last moment I was drawing the diagrams trying to explain that if perturbations were there, they would initially be normal in the very simplistic sense, and perturbations can be, if there is only one constraint which is being perturbed, you will basically have the univariate distribution, you will solve it using the standard normal deviate, and your life is done. And obviously, you can consider them in the simulation part, because normality being a very nice distribution, you can utilize the standard normal table and solve it accordingly. Now, the second question which we went into the next level was that if normality was not it was there, but if there were more than 2 normal distributions, obviously will the multivariate normal case, and the problems could be solved, and I was drawing the diagram accordingly. So, which I will start now explaining as required. So, this diagram where I stopped in the end of 24th lecture. So, now consider at point C. Let me assume that the line BC and CD are orthogonal, even though in the diagram they are not being shown an orthogonal, they are orthogonal. So, consider orthogonality such that you are standing in front of me, the plane which is orthogonal, and there is 90 degrees. So, perturbations are there and a normal distribution is coming from your side, a normal distribution is coming from exactly orthogonal plane, and both of them have the same variance. So, they pass each other. So, if you consider the overall common area, it will be just a simple standard bivariate distribution, for which if you take the slice, if you look from above, they are just concentric circles. You cut them concentric circles, because the variances, if you consider from the plane side where the first distribution coming, which is normal, and from the orthogonal side, both of them have the same variance. Now, so which means that in the 2-dimensional case it is a circle, in a 3-dimensional case it is a sphere, all the variances are same and they are orthogonal. In the higher dimension they would just be hyperspheres, and the areas would basically dictate something which I am going to come with in 2 minutes. Now, consider in the 2-dimension case they are orthogonal, but they are normal distribution, but 2 different variances. So, consider the one which is coming from your side has a lower variance, and the one coming from the right hand side, orthogonal from the right hand side, which is where I am pointing my hand, this is orthogonal and a higher variance. So, when they cross each other, and if you look from the top, they would be ellipse. That means, they are exactly look like a rugby ball, which is placed in a sense where the elongated surface is facing from your side to mine side, because the variance is higher and the major axis is this. So, if you are looking from the top, there are ellipses. Now, just reverse the scenario where the distribution, normal distribution which is coming from your side has a higher variance than the normal distribution which is coming orthogonal to this, and they cross each other, it will be again the same rugby ball, an ellipse, but where the major axis would now be parallel to what I am standing and the parallel to your face. Now, extend that to the case where the surfaces where the normal distributions are interacting, they have the same variance, but they are not orthogonal. So, obviously, it is not the same way how you will basically perceive the ellipse with the major and minor axis. The major and minor axis in the initial two cases were 90 degrees to each other, now they would not be 90 degrees to each other. In the case when you have the variances difference. Now, if you extend that to the case of higher dimension, it is basically an ellipsoid, and a higher dimension ellipsoid would basically give you an idea that trying to find out the common area. Now, what is that common area? I will come to that. Is the common area where the overall probability would be maintained for all the combinations. So, if when I am saying probability of a multivariate distribution being less than x, x is also a vector, is equal to some alpha value, it would mean the common area where all the ellipse or where all the circles or the hyperspheres, basically the total common area of the hyperspheres or the sphere is such that it will basically be true for all of them inclusive. Now, consider that. So, with this we have considered that normality, if it is done, how we will basically be tackle it. So, in general, if it is normal, one dimension no problem, two dimension bivariate orthogonal no problem, higher dimension no problem. Variances are same different no problem. If the variances are same or different, but if they are not orthogonal, you can basically transform them into orthogonal surfaces and use the concept of normality and proceed. Now, what happens in the case if they are themselves non-normal? So, obviously, trying to find out a very weird shape is coming from your side, depending on if it is an exponential distribution or whatever it is, and another orthogonal plane, another distribution is coming, then the common area is no more a sphere or a circle or just like a balloon, it is not that. So, finding out the common area where the overall probability will be satisfied depending on the constraints would be very difficult to calculate. You can visualize, but it will be very difficult to calculate. So, how it look is exactly the diagram based on which when I stopped was what I was basically trying to point out. Now, I will with this discussion whatever I had, I will come to the diagram and explain it and then go into the sensitivity analysis. So, these two blank slides which I mentioned I thought I will draw, but I will skip and then come back if required. So, this is the diagram which I was talking about. It looks a little bit complicated, but is not. Whatever I have discussed, if you have listened to it carefully, you will understand. So, and this again I am doing it in a 2-dimension one, it can be extended for a higher dimension, you will understand. So, along the y axis we have x1 variable, along the x axis you have the x2 variable, and consider I would not be drawing too much because as such the colors are very close to each other, it will be difficult for you to differentiate, just I will hover the electronic pen. So, consider this, and this the green yellow color I will just hover it. So, consider the yellow colored pen which is hovering, this green bold line is the are the two constraint, and in the initial example which I considered they were straight lines because they were linear, but they are not linear, that does not matter. So, this is the first constraint which is given by G1, x1, x2 are the decision variables, d1, d2 are the deterministic one, p1, p2 are the parameters which are probabilistic. For the time being, consider the probabilistic part is not there. The second constraint is G2, x1, x2, d1, d2, p1, p2 are not there, still I am writing and is greater than b2. So, in case if they are greater than b1 and greater than b2 and they are deterministic, the common point which is here, which is a red dot, if you can see as I am hovering the electronic pen, is the deterministic optimal solution. So, if you solve the problem using any of the method which you have considered, you will get the answer, give the result, find out the objective function, whether maximization, minimization, and be happy, and your work is done. Now, what happens if by itself initially the constraints are non-deterministic due to the fact that P1, P2 has come, which means if you go back to one of the problem, that it was that the plant 1, plant 2, plant 3 had some different constraints on the maximum capacity. Similarly, for machine 1, machine 2 number of hours was 8. Now it is no more 8, it is changing. Like consider that due to the policies of the company, you can either use 7 hours or you can use 9 hours. Some distribution is there, some probability for the number of hours being utilized for machine 1 is there. So, in that case there would be a perturbation of the green line both inside in the feasible region and outside in the infeasible region. So, obviously infeasible region would not be true for the deterministic case, but for the probabilistic case some part would be infeasible, which was initially would be considered as feasible, which means the overall if I consider normal distribution. Now, the one which I just drew considering the normal distribution for the constraints, if they coalesce or they come together, then the overall common area would be a circle for a 2 dimension one as it is the case, or a sphere in the 3 dimension one if you have x3 also vertically up, and the common area would, or with the center of that sphere or the circle would basically be the non-deterministic or the probabilistic solution, and the overall area it will cover will give you the probability or the reliability of the result. So, depending on the area it is covered, if it is 90%, 92%, 95%, it will give you how good or bad your results are, how reliable your results are, how robust your results are. Now, consider, as I mentioned, the distributions per se are non-normal, and how I am mentioning that and how I am trying to basically portray that is in these two red marginal distribution which I have drawn. So, the dotted lines which were there, it basically the dotted green one and the dotted this more small dotted one and large dotted ones are basically the perturbations which are happening for the constraint, and it is in the 2 dimension one, it can be done in higher dimension also. So, this green, so this red color distribution is the marginal distribution of x2. Similarly, considering that you have fx2, similarly the red one which you have, and they are orthogonal. Remember, for the time being we are considering them orthogonal to be true for x1 and x2 variables, and this red one which is along x1 is the marginal distribution of x1. So, if they were normal, as I mentioned, I am again repeating it, common area is a circle, sphere and so on and so forth, hypersphere depending on dimension. Now, if they are not normal, the overall contact area or the common area would be a very weird shape. So, as the probability increases and decreases, the reliability, the general area which you see where I am hovering my this electronic pen, the yellow one initially is the probability based on the fact that the center point which is here, which is the center of gravity or the common point of the CG, or say for example the mean value of the common between both these distributions. So, one is coming from 90 degrees, another is going here, they meet, and the center of gravity or the center of this joint distribution of f x1 x2, which I am not able to derive, but I am only able to give you a simplistic visual view for that. So, this point which is the blue one is the reliable robust solution with some level of probability depending on the value of reliability which I put on the perturbation of constraint 1 and constraint 2. So, constraint 1, constraint 2 can be of different reliabilities, but I basically find out the common value based on which I can find out the common point. So, this is this solution which I have, the blue one is the center of gravity, and as I increase and decrease my level of reliability, or as the perturbations increases and decreases, the movement of the first constraint and the second constraint, deterministic part would be far wider inside the feasible region and outside the feasible region, but obviously we will only keep our limitation discussion to feasible region. Hence, the area will increase or decrease depending on the perturbation, and it may be possible that as the perturbation increases or decreases, or as the constraint changes, the loci of that point or the center of gravity would basically keep moving more inside the feasible region obviously, such that it will give us the probabilistic point based on which you can say that with certain level of reliability our answer will be true. That reliability is basically coming from the value of beta. So, this as I mentioned is the loci of the reliable robust solution, it will go in more inside depending on the level of reliability which we will assign for that. Now, if it is 3 dimension one, it will be easier for you to understand if the figure which is there and drawn. So, it will be a very weird shape which will keep expanding and contracting depending on the level of beta which I am assigning for the answer as such. Now, this diagram which I have already discussed I have told verbally, but I am coming to that. So, consider that if it is a normal case. So, this again I am going back to the normal case or the symmetric distribution. So, you have x2 along the x direction and you have x1 along the y direction, and your feasible region which changes depending on the perturbation which is there. So, the blue line which is B1 and the blue line which is A1, their common point, the deterministic one was where I will just mark it, where this deterministic point is, but due to perturbation it moves inside, and the orthogonality of the constraints are not there. If you check here, they are not orthogonal. So, obviously the ellipse would be such depending on the variance being higher and low in whichever direction you are considering, whether in the x1 direction or the x2 direction. The loci would basically move inside in order to basically portray that how the reliable solution moves and what is the overall common n area. Now, if you consider the red lines of A and B, the deterministic point would be the common area which is this. So, say somewhere here. So, I will basically use a different color somewhere here. So, because the colors is blue, it is difficult for you to understand, and again the loci would move in such a way that the feasible region obviously would be met, and the overall area, the red one or the blue one, the whole shaded region would give you the reliability of that point. So, depending on 90%, 92%, 95% what you have. Now, if the variances of in this case the variance of x1 is larger in diagram 1, which is the leftmost panel, and in diagram 2 you basically have the variance of x2 is higher, and obviously here the concept of normality or the orthogonality is being considered to make our life simple. So, as A and B for the red part, when there is one solution depending on the reliability, and the A1 B1 part depending on the perturbations of the reliability changes, you have two different deterministic point and they move, the loci moves inside the feasible region to give us the idea how the probabilistic value for the solution changes and which areas you will basically have in and around that probabilistic point, such that you are able to say that with certain level of certain reliability 92%, 95%, whatever it is basically being determined the value of beta, that you are sure your answer is correct. Now, third panel which technically should have come on the left part is when both the variances of x1 and x2 are same and they are orthogonal. So, if they are same, so then trying to find out the center of gravity for the point where again the loci would move inside the feasible region and the overall area would be basically given by the level of reliability which you have. Now, remember one thing, reliability of the beta. So, if you remember, the beta value is probability of x in a univariate case your probability of x less than equal to small x is greater than equal to beta or alpha, whatever it written. So, if you consider the value of beta, it is basically the overall area which you have inside the circle or the ellipse. Now, it can also be portrayed that as a circle of a certain radius, where the beta value can be utilized to draw the radius, and it will give you, because you remember the beta value would always be between 0 and 1. So, that will give you the unit circle maximum or a circle of lesser size, such that it will give you a perception that how the circle will be drawn or how the ellipse will be drawn, depending on you are trying to take same variance or higher variance for either x1 or x2. Now, what we need to do is that we need to find out the optimum values of the decision variables under the set of constraints, whatever we have been discussing. And here the case is the probability of GJs, and it can be HKs also, but I am just taking one set of constraints only in order to portray that. Probability of GJs x, d and p, where x is the decision variable, d is the deterministic one, p is the probabilistic one, is greater than equal to or less than equal to bj's for j is equal to 1 to capital J. So, plotting the probabilities. So, you are plotting the probabilities along with the constraints and would provide us some information of how the values of betas are there. So, I plot the values of the function GJs, and then I try to find out that as the probability changes, how the overall surface changes. So, it will depicts the instance when the area under the curve is less than, greater than, less than, equal to, depending on greater than sign, equal to sign, less than sign for the value of f. What we are considering is that if you have a joint distribution, what you want to find out is that the multivariate, I am not talking about the normal case, the multivariate distribution of the cumulative distribution is such that the overall probability is less than equal to, greater than equal to, or less or equal to the value of beta based on which you are trying to process and trying to find out. So, because why it is a multivariate distribution and you are taking capital F of x is that you are trying to find out the joint distribution, not the marginals. So, they would basically be coming at the joint distribution, where all the probabilities have to be met. Hence, you would basically count from either the left hand side if it is less than, or if it is greater than, you will basically consider from the right hand side. So, what you will do is that given a predefined performance level, so the performance level will basically be coming from the problem formulation which you have beta. You will be interested to find the probability or the reliability such that it is greater than, less than, or equal to a pre-specified performance value, which would be given by the fact that you will basically do the orthogonal transformation and find out the GJs to the power beta, which is basically greater than, equal to, or less than, equal to, or equal to 0. So, what you are doing is that you are trying to transform beta onto the left hand side and trying to find out the probabilities which will satisfy that. Based on that, you will basically find the answer. So, the perturbations are now being considered, where if you consider Ax is equal to b, greater than b, less than b, or equal to b, you are transforming that b, the vector, onto the right hand side, putting a 0 on the right hand and on the right hand side, and then recalculating to find out what is the probability based on which you can solve. So, the idea of inverse reliability will be utilized, the formulation of which will hold true such that g suffix j for each of these j's to the power beta is greater than, equal to, less than 0 is satisfied, where they would, the g beta would give you the percentile performance of the constraint such that the unique transformation which you are going to do from the probability sense to the percentile conversion would be true, and this one to one transformation will give you the values of g betas based on which you can do the calculation. So, once you are considering that, you will consider the objective function as when we are doing the perturbation. So, when you are doing, so the perturbations which I mentioned was from the sensitivity analysis, but they can be different ideas of perturbations. So, one can be, you can consider the objective function as a point of cost benefit analysis. Hence, one can choose a certain direction for inequalities. So, if it is a cost or a benefit, so if it is a cost, you will basically consider them as negative. If it is benefit, you will consider them positive. So, maximization problem will be converted into minimization problem, or minimization problem to the maximization problem. Obviously, you will be asking that does it seem that we are trying to do a primal dual problem? The answer is that in order to find out the solution, I did tell you that number of constraints becomes the number of variables and vice versa in order to for the solution of the problem, but here we are only considering from the point of view of sensitivity analysis in trying to do the problem. Hence, one can choose a certain direction for inequality constraints, replacing the greater than or the less than type, and then basically replacing the plus by the minus, minus by the plus. We can also replace the inequality as a resource supply and demand in the less than type or greater than type. So, if it is a factory where it has to supply 20 million tons of, say for example, fertilizers, so obviously the constraints would be, depending on how you have problem, it will be a less than type, in the sense that you will definitely utilize those amount of products. So, it is like this. I have a factory which needs definitely 20 million tons. So, our constraint will be formulated in such a way that the constraints would be definitely greater than equal to 20 million, because any product or any amount coming less than 20 million is not allowed. Any product coming exactly equal to 20 million or more than 20 million would be allowed, based on which we can formulate the problem. So, it can be like you have an inventory storage, and the number of amount of goods you can store is maximum, say for example 20 boxes. So, any level 20, 19, 80 is possible, but any level 21, 22 is not possible. So, obviously, you will formulate the problem accordingly such that constraint would not be violated, considering the practical problem which you are facing or the constraint which you are facing. Sensitivity analysis will try to compute. So, what we considered is that, well, I am going to come to that. Sensitivity analysis will try to compute the picture of studying how results would vary by changing the parameter values. The parameter values is that D and P, what we consider, if we perturbed, how they will change. Our main task would be to study and comment about the sensitivity of the optimum solutions considering change in the input parameter values. So, as the input parameter values are changing, P or D, how the constraints are shifting inside. If you remember the last diagram which I drew, and the fag end of the 24th lecture, based on which I started the 25th lecture, the constraints were linear. As the constraint changes, so they can either move inside, that is why your feasible region will shrink, or they can move outside, depending on you are trying to increase the constraint levels. Like in the machine problem, I said you can use either out of the 8 hours, you can either decrease it to 7 hours or you can increase to 9 hours. So, 7 hours would mean that your overall constraint is decreasing. And if it is decreasing, remember also, or it is increasing, remember also that would have an effect on, leave aside the answer, that will have an effect on the slack and the surplus variables, based on which we can say that yes, it is possible that if we basically reduce one of the constraints or increase one of a constraint, our excess material or more materials which we will need can be made to 0, such that even if the optimal limit is not used, yet we are able to use our resources to the maximum possible extent. With this, I will end the 25th lecture and continue more discussion about the sensitivity analysis in the 6th week, starting the 26th lecture. Have a nice day and thank you very much.